Welcome everybody in the lecture hall, welcome everybody in Zoom, welcome everybody from the future. We're going today to continue looking at MapReduce, which is the first processing lecture of the semester. So now we are getting into the serious things that we are actually processing the data that we've been storing on all of these layers. And MapReduce is basically the first generation of massive parallel processing, right? So it's already almost 20 years old now, but all the modern parallel processing frameworks, they are still based on the same ideas, right? So then we look into Spark, but we'll see that many of the physical details that we saw in MapReduce are actually also just as relevant for Spark. So this is why I'm including it. It's a way to start smoothly with parallel processing, right? So we'll have multiple weeks looking into these things. So MapReduce is called that way because of map and reduce. These are the two phases. The map phase is what we've been doing yesterday with the first 8 volunteers who were counting the Pokemons like this. And the output of the map phase is these key value pairs with the Pokemon without S here were keys, and the numbers here were the values, right? So implicitly, you could imagine that these were also key value pairs just every time with the number 1, right? You could imagine, or with a null or a dummy value, but basically you can assume that this can also be seen as key value pairs. So that was the map phase. The reduce phase is when we gather and group together all of the key values that came from here. This is where they came from, but now we put them all together and group them by key. So all the Pikachus here, they all go to the same reducer, and the reducer in that case does the sum of all of these and issues an output key value pair with, in that case, 8. So Pikachu 8 is the output of that, and then we get, in that case, this output, and then the other reducers do the same with their keys. What is important is that I didn't say anything about the map function or the reduce function in the sense of constraint. In that case, for Pokemons, we just output the counts and we sum them up. But in general, that can be any function you want that you apply here to every key value in the input. And the reduce function can also be any function you want, right? The only thing is that when you apply the map function, you return 0, 1, or more intermediate key value pairs. And when you call the reduce function on a specific group of intermediate key value pairs with the same key, you output 0, 1, or more key value pairs. That's what the map and reduce functions are doing, right? And so if we summarize the whole logical scheme of what is going on, we have these input key value pairs, right? We map them through the map function. Each key value here is mapped to 0, 1, or more intermediate key value pairs, but then we flatten everything again. Then there is a sort happening. We sort by key, and then we partition again where all the keys that are the same are together. This is the same key, this is the same key, this is the same key. It's all grouped by key. And then we apply the reduce function to every group that has the same key, right? So all the same key, and all of them that have the same key are in here. You cannot have them over several groups, right? For whom is that clear? This grand scheme of things with MapReduce. All right. So now that we've described the logical details of MapReduce, I'm going to go into the physical details of how this is implemented today. So the first thing that is important to know is that MapReduce works on many different layers. It works on top of S3. It works on top of HDFS. It works on top of HBase. It also would work on top of your laptop on your local file system, right? Maybe not as fast because you would be bound by the speed at which you can read from your local drive, but it also would work on your laptop, right? So it works from pretty much all of these places, even Azure Blob Storage, Google Clouds, GFS, which is the Google file system, the original one. So all of these places. And the reason it works well, especially with HDFS S3 Azure Blob Storage, is that this is stored across the cluster on multiple machines. So the one problem that we solve with MapReduce is that since we read in parallel across plenty of machines, the speed, the number of bits we read per second is much higher than on a single machine. Imagine, for example, that you can read on a single machine 100 megabytes per second, 100 megabytes. Now you have 1,000 machines, you can read 100 gigabytes per second, right? This is the power of MapReduce. And the one reason why you want to use MapReduce is because you cannot read the bits fast enough on a single drive. So we do the processing, so the map phase, because we start with the map phase, distributed over all the nodes. And typically, it's going to be the same machines that are going to do the maps as the machines that are the data nodes in the case of HDFS, right? So it's the same machines that store the data and that process the data. So let's assume now we have several terabytes of data, maybe even petabytes, but already with terabytes, you get a performance advantage over a single machine, and thousands of nodes, right? So you remember the architecture, HDFS, that's the name node and the data node. You remember HBase, same centralized architecture with the HMaster and the region servers. Well, guess what? In the first version of MapReduce, it's exactly the same architecture. You just have to learn new names, that's all. But it's the same good old centralized architecture. So the coordinator node is called the job tracker, and the worker nodes are called the task trackers. So what's important to know is that now we have 3 processes running on every machine, right? On the coordinator node, we have on the same machine a name node process, an HMaster process, and a job tracker process, all running on the same machine. And we have on the same machine a data node, a region server, and a task tracker, all running on the same machine. All right, so far so good? And what happens, and that's the power of, I have this trick that some of you told me, if you want to see what's happening at the bottom, I need to click here, open the chat window, and close the chat window, and it doesn't work anymore. It used to work like this, like I just had to do this, and then at the bottom, it would just disappear. Yeah, maybe there was an update. But anyway, you can still see task tracker, right? So we have the name node and the job tracker on the same machine, and the data node and the task tracker on the same machine. So we store the data on the same machines as we process them. I didn't put here the HMaster and the region server, but it would be there as well if you're using HBase, right? I'm going to focus on HDFS for the most of the lecture. There is a name for that. That was actually a buzzword 15 years ago. It's bring the query to the data. The data is stored there, then bring the query to it, and query the data right from where it is actually stored, right? So this is the reason why we have these task trackers on the same machines as the data nodes. So what's going to happen is that, of course, the blocks are stored 3 times with replicas, right? There's 3 replicas of each block. But in an ideal setting, now I'm looking at the ideal case, I'm going to have my file stored in that case in 7 blocks. And I'm looking at 1 replica of each blocks, 1, 2, 3, 4, 5, 6, 7, even 8 of them. I'm not sure what I did with the last one. Yeah, I missed the color. But anyway, these are my 1 replica of each block. And I'm going to focus on these splits. And I'm going to execute my map function on all the key values that are in these splits, right? So my map function will apply to all the key value pairs in there, all the key value pairs in there. Then on that machine, a different CPU will process the map function with the key values in there. On this machine, the key values in there, and so on. So you see that it will nicely work in parallel, because in that case, the map function can directly read from the local drive. There is no network communication in there. Who sees that we don't need any network for doing it in parallel? Right? Very good. So, by the way, you notice that I used the word split. I told you block, split, chunk, partition, shard, and so on. There's all these words that people tend to use interchangeably. For HDFS, we say block. For MapReduce, we say split, right? So we call it a split. A split corresponds to 1 map task, as we will see, right? It's one unit of execution of MapReduce. So it's called a split, but more or less, 1 split corresponds to 1 HDFS block, right? So we process 128 megabytes at a time. All right. So now I represented here what are called slots, with M for map and R for reduce. What is a slot? Well, you can consider that it's a virtual core on your machine. So you know that now when you buy machines, the CPUs have multiple cores, right? 4 cores, 8 cores, 16 cores, 24 cores, 32 cores. And with hyper-threading, virtually you have double that, right? If you have 8 cores on your laptop, then you can in fact execute 16 parallel processes, right? Who heard of hyper-threading? Some of you, okay. So typically we multiply by 2. It's double the number of physical cores. So here I represented, of course, I could not put 16 of them on every machine without overloading the slides. So I only put 2 or 3 of them on every machine. But basically imagine that every one of these is a virtual core. I'm going to be using every one of my virtual cores either for mapping or for reducing. So here I had 3 cores, 1 core for mapping, 1 core for mapping, 1 core for reducing, mapping, reducing, and so on. And what's going to happen is that these CPU cores are going to execute the map function on the key values in here. Maybe this one will process these, and this one will process these, right, on the same machine. Now, this is the ideal case that the data is on the same machine, but it's not always going to be the case. But in that case, it's not a problem. Then you go over the network, right? If some of the data isn't stored on the same machine, here I put an example of a mapping slot, a CPU core that cannot read directly from the disk because there is no replica. It's just going to go via the regular HDFS protocol to the name node and so on, and get the block from the machine on its right. Okay, so now we launch the first phase. It's called the phase, the map phase, where we call the map function on all the key values. And now this is all done with the CPUs, the virtual cores of the CPUs, and in the memory, right? It's the RAM, the working memory on the machine, where we store all of these intermediate key values that we generate, right? So we go through the key values, call the map function, and keep the intermediate key values that are generated by the map function in memory. However, it might happen, and actually it will often happen, that you will fill the memory with intermediate key values. Maybe you produce so many of them that the working memory is not good enough to store all of them. What happens? Guess what? The same thing as in HBase. We spill all of the key values in sorted order of key. We sort the keys, and we spill it all to the disk. In fact, that's pretty much a flush. You can consider it a flush like in HBase, right? It's key values, sorted, we maintain them with some tree structure in memory in a sorted order, then we flush in linear time all of the key values to disk. Then we continue to fill the memory. If it's full again, what do? We flush again, okay. And if we have multiple files, we compact them, exactly. So you see everything you learned for HBase, now it's useful here too. So we can manage that with the log structures merge trees. If we keep producing so many key value pairs that it doesn't fit in memory, we just store them in a log structures merge tree on the disk. Next, I'm done with the map phase. I have produced all of my intermediate key value pairs. Some are in the memory, some are on disk. Now comes the shuffling phase. What is the shuffling phase? Well, the reduce slots will need all the key values grouped by key, right? So maybe this reduce slot right here, is responsible for all the keys for Pikachu, let's say. So this reduce slot will have to fetch all the Pikachus from here, from here, from here, from here, from here, from here, from everywhere, right? So this is, remember in the lecture hall yesterday, this was the part where you were exchanging the key value pairs. That is quadratic. It is not linear. So this is the part that you actually have the bottleneck because of the network. There are so many connections happening between the machines, but we basically ship the key values to the machines that run the reduce slots, but in a way that the keys are grouped together, right? So if that actually, maybe I'm too far away. This is the reason why it doesn't, yeah. So basically, if you're the reduce slot, one of them, and you're responsible for some keys that you need to reduce on, then you have to connect to every single other machine and your own machine as well, and ask politely for all the key values that correspond to the keys that you are responsible of. Since we said that this is all output to disk or in memory in a sorted fashion, it's quite easy to retrieve the groups of keys because they are stored together, right? So it's not like we have to go random access on the disk. It's all nicely grouped and sorted. All right, but we need to connect from every machine, to connect to every machine. And this is all done over HTTP, right? So there is some HTTP server running on all the map slots, and the reduce slot connects to the map slots and gets the values. It's not the other way around, right? You might have thought it's the map slots that send the key values to the reduce slots, but no, it's the opposite. It's the reduce slot that connects in order to get the key values that it needs. All right? So now maybe all the Pikachus are in here, and then the Pokemons are nicely grouped. Yes, there is a question over there. It works. There you go.
Isn't it inefficient if every data node has to communicate with all the other data nodes? Couldn't there be one data node where it collects all the maps and then it reduces itself?
So it's not the data nodes that communicate, right? Here, it's really the task trackers that deal with this. The data nodes, they are only responsible for storing the replicas of the blocks. And the data nodes will only communicate in the replication pipelines, right? When they make copies of the block. But the task trackers, indeed, the task trackers will all connect to each other. It's a quadratic number of connections in order to ship over the key values. The key values, note that the intermediate key values stored on disk, it's not on a GFS that they are stored. It's on the local disk of the machines, right? Was there something else in your question, or?
Couldn't there be one sort of centralized task tracker to connect with all the other task trackers and then reduce?
I'm sorry, I didn't understand.
Couldn't that be like, oh, maybe it's better like this?
Yeah.
Couldn't that be like a centralized task tracker? So there's only n connections rather than n squared?
I see. No, because you would have a bottleneck, right? So okay. You cannot have a single centralized task tracker, because if you're manipulating billions or trillions of key values, it doesn't scale, right? So this is why you really need to have this in a distributed fashion. Right. And the shuffle is basically something we need to do. So we need to have a shuffle, but as we will see later, we will want to minimize the shuffling, right? You will want to structure your queries to avoid having too many shuffles, but you will very often need the shuffles in any case. All right. Okay. So now we are reducing. So now the map slots become idle, and the reduce slots are going to start processing the key values. And at the end, for every reduce task, every group of intermediate key values that we call, we are going to output files. So maybe this reducer right here outputs part 1. To HDFS. This reducer here output part 2 and part 3. This one output part 4. It had a bit more. This one output part 5. This one output part 6, and this one output part 7. Right. So they all write to HDFS in parallel. What's very important is that they write different files on HDFS. Right. They cannot be writing to the same file because it's locked. Remember that when you write to a file, you have a lock. But since they write to different files in the same directory, this all works nicely in parallel. For whom is that clear? All right, very good. So then at the end of your MapReduce query, you can go to HDFS, you will find your output directory, and you will see all of these files, part 1, part 2, part 3, that contain the output of your query. And then you can run yet another MapReduce job that will take this output as its input, so you can chain the MapReduce jobs with each other. Okay? So now I'm going to go into input-output formats, say a few words. Why? Because I told you that for MapReduce, everything is a key-value pair. But as you know, not everything in the world is a key-value pair. So we need to find a way to actually interpret them as key-value pairs. So basically, we can do it from and to tables and from and to files. I mean, we can have input or output as tables in HDFS or even in a relational database, and from and to files on HDFS, S3, and so on. In the case of tables, it's actually not too complicated because there's the notion of primary key, right? So the key is going to be the row ID in the case of HBase, and then the value is going to be the rest of the columns, right, in one or more column families. For a relational database management system, it's the same, except that in the general case, we might have more than one column that together are the primary key of the table, right? In that case, the key for MapReduce is the compound key across the primary key columns, all right? So we create, for each one of the records in the table, a key value for MapReduce, where the key is the row ID or the compound primary key, and the value is all of the other columns. And now MapReduce is happy because it sees key values, right? So now it can process them according to its paradigm. For whom is that clear, how we can read from a table? Okay. And now from files, there's different formats. We'll have files that are just text. just text, lines of text, we'll have files that are in essence already in some sort of key value format, for example, with a space that separates on every line the key from the value. And we have sequence files that are binary formats that store sequences of key values, right? So they were invented together with MapReduce. So let's start with text. How can we interpret? Imagine you want to, I don't know, parse the complete works of Shakespeare or Sherlock Holmes. How do we interpret this as key values? What happens very naturally when we process in parallel like that is that we are going to split based on the lines. So every line of text will give us a key value. And when I say line, I mean with the \r\n, right? So the line feed and the new line separators that you look for, and that separates the line. Every line gives us a key value. Now, what do we take as the key and what as the value? So the value is, we usually take the line of text, right? That's the value. And for the key, we are going to use the offset from the beginning of the file, right? In bytes. So how many bytes have elapsed? So this says basically it's the beginning of the file, offset 0. This is offset 18. So there's 18 characters here and then here. So that's an offset of 18. Then we have 27. So that's the total offset to arrive here, and so on. So now you have key values. And now MapReduce can process this because these are key values, right? And you have all the text information nicely contained in the values. Then there is another way of doing that, that is interpreting the lines of text as key values, but here you assume that there is a special character. In that case, I put this field circle to indicate the separation. In practice, it can be a space, it can be a tabulation, it can be pretty much any character you want, a comma, a semicolon, but you interpret it in a special way that separates the key on the left and the value on the right, the key on the left, the value on the right. So you see, this is how you interpret them. If it doesn't exist, then you just put it in the key and nothing in the value, and so on. So you see, it's just a different way, right, of interpreting these as key values. Is there a question on Zoom?
When you speak about the input to the MapReduce algorithm, do you refer to the data processed or to the query? Which of them needs to be converted into a set of key values?
So what we convert, so this is really, MapReduce only understands key values. That's the only thing that MapReduce can process. So when you open the files in order to apply the map function, you need to do this pre-processing. Before you can apply the map function, you need to interpret the lines of text in this way as key value pairs. So it's really when you open the file and start reading that you do this interpretation. It's not done by HDFS, it's done by the MapReduce library, but before you start calling the map function, right? And it's done on the fly, right? As you process the data, you read it, you turn it into key values, and then you feed it in the map function. Did it answer your question? Yeah, awesome. So let's apply this to a simple use case.
Another question?
Yes, go ahead.
Also, does a split usually only represent a single HDFS block or multiple? Because what happens if data that would be interpreted as a key value block is spread across two splits? How would we deal with this in MapReduce?
This is very smart, and you're anticipating on something that I will come back to. The rule of thumb, in general, is that you want a split to correspond to a block. You want a MapReduce split to correspond to an HDFS block. That's the rule of thumb. It doesn't have to be. If you prefer to have 2 blocks or 3 blocks in a split, you can. If you prefer to have half a block in every split, you can. Maybe it's not efficient, but you can. But the rule of thumb is 1 block, 1 split. You're absolutely correct to remark that the blocks strictly separate bits. It's exactly 128 megabytes. So you might end up with a key value, the last one, that starts in a block and ends in another block. And this is indeed a problem. And the way it's handled is with a remote read. You basically will finish maybe asking from another machine these last few bits. Then you will not ask for the full block, but just a part of the block to get the last bits. So that's the very clever remark, and it's really nice that you already noticed this now. Okay. Did it answer your question? Awesome. So let's take an example. let me take the complete works of Shakespeare, and I want to count the frequency of each word. How many times every word is appearing there, and maybe build some sort of histogram of the most used word in Shakespeare's work. How could I do it with MapReduce? Well, let me just make this interpretation here that I'm parsing the lines in this way, that every line of text gives me a key value. So now we need to come up creatively with the map function and with the reduce function that do what we want and output the histogram. So the map function that we could use could be that we tokenize, it's called tokenizing. Those of you who were in information retrieval, you might remember this. So we tokenize based on spaces, for example. So now I'm creating key value pairs, and every token, every word gives me a key, and then I put a 1 that says it's occurring once. So now I have lorem 1, ipsum 1, $1, and so on and so on. So on the right, you see my intermediate key value pairs that are produced by the map function. And you can see that every input key value can be mapped to several intermediate key values. Could also be 0 if I have an empty line, could be just 1 if I have only 1 word on a line, can be 10 if I have 10 words on a line, right? So this is my map function. And the reduce function, it's basically like the Pokemon counting, is that now I can call a sum or a count, because it's all ones anyway, so it doesn't matter if I count or if I sum. So 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 gives me 7, and the reduce function will output lorem 7. And then who sees that my general output at the very end will be exactly all of the distinct words that I found in Shakespeare, followed by the frequency. Who sees that? Awesome, perfect. So this is an example of MapReduce. Instead of counting Pokemon, we count words by frequency in a word. And you can actually try this if you want. It's really a simple use case. And basically, whatever you want to do, you need to figure out the map function and the reduce function that does the job. Yes, maybe I can bring the microphone.
What happens if we're trying to count the words, the occurrence of each word for something super big, like the internet something? Will we have to run, because the partition will be huge, right? So we'll have to run another MapReduce on top of that, or is there any other way to, like, yeah.
So if I correctly understand your question, what you are worried about is that the number of a specific word like the or A or B could be so huge that it creates a huge bottleneck in terms of the key value pairs. We have ways to actually improve this. I'll explain one if we have time today or maybe next week. It's called combine, with a combine function that we can compress a little bit the intermediate input-output. And if with doing that, it still doesn't solve the problem, then it means that you fall back to the user who has to figure out a better way. You have to figure out another way of doing that, because indeed, you have to design the whole thing in such a way that the number of key values with the same key still fits on a machine, because you want it to be possible to be executed by a task tracker.
Okay.
Did that answer your question?
Yeah, thanks.
Awesome. And I'll explain a bit later the combine function. All right. What about another problem? We want to filter lines. I want to output all the lines that contain a specific word, like internet or Hamlet or whatever I want. So I'm interpreting the lines in this way as the input key values. And then as the map function, I can do simply a filter, meaning that if the words that I'm looking for are in there, I output as an intermediate key value an exact copy of the input key value. I just forward it. It's an identity. And if the line does not contain the word, I just output 0 intermediate key values for that. So you see that now my intermediate key value pairs are a subset of the input key value pairs. And the reduce function is the identity function in that case. I just do nothing. I just forward to the output at the end, right? So this is what I've just done. Now, you might have just had the realization that in spirit, what we've just done here on top of MapReduce was a selection from the relational algebra. If my input were not a text file, but a relational table, and I would have a predicate and I keep the records that satisfy the predicate, I have just implemented the where statement of SQL on top of MapReduce. This is exactly why we are doing all of that, because in the end, we'll have the whole SQL. right? But on a higher level than that. So if we just had a selection, what about a projection? Let's try to do a projection. I'm going to try to do a projection just for the sake of showing how it's done, not on top of a relational table, but assume we have JSON, right? Imagine that I have billions of JSON documents, one document per line. It's called the JSON lines format. So every line from MapReduce perspective, it's just text. MapReduce doesn't know anything about JSON, so it's just a bunch of text. So it's going to be interpreted with the some numbers or offsets. In that case, I just put integers, but it doesn't really matter. And then the values are my JSON documents, but it's text. It's only text. We don't even know it's JSON. Now, my map function needs to do this. How do we do that? Well, imagine you're using Python to implement your map and reduce function. You know that in Python, you can parse a string as JSON. So we just need in Python to parse that as JSON. Then we can, in Python, remove everything we don't want or only keep what we want, ID and country in that case. And then we serialize it back as text and we get our output key value. What's important here is that we needed to do it all in Python or in Java or in a host language because MapReduce doesn't know JSON, right? But assume I write that code in Python, I can do this. The reduce function, what do I need if I want to project? What reduce function will I have? The identity function, right? I don't need to change anything. I already have what I want. So the reduce function is the identity function. Who agrees that we've just done a select ID country from the data? That's what we've done. So now you could implement a chain of that with a select and where. You could do two MapReduce jobs, the first one that filters, the second one that projects. And in the general case, you will not be able to do it in a single MapReduce job, but maybe 2 or 3 or 10 MapReduce jobs. So this is a projection. There are many, many other things you can do. You can index the entire internet. We actually did it in information retrieval. We index the entire web with MapReduce. You can also implement matrix multiplication in MapReduce. So very large scale, even machine learning kind of things that you can do in this way. It might require an iteration with several jobs, but you can basically do it. So it seems I'll be able to answer your question on the optimization because we have enough time. So let me do it. In the general setting, I have this map function. So the mapping phase that goes from the input to the intermediate key values, and the reduce phase that goes from the intermediate key values to the output key values. Mapper and reducer are just normally the name of the Java classes or the Python classes that you want to use to do that. But I'll explain to you next week that you should not use the word mapper and reducer when you speak about MapReduce. It's a very bad idea because it's very confusing. So this would just be the name of the Java classes that implements the map and reduce function. All right. Is there any way that we can have less intermediate key values? We can compress the intermediate key values. Does anybody have any idea? When I was counting the words, for example, and I had plenty of ones all over the place, how can I have less data shuffled around? Yes? Exactly. Yes, exactly. So I'm going to repeat what you suggested. You suggested that during the map phase, we already start summing the key values with the same key to reduce their numbers. This is exactly the right approach, and this is called combining. So the idea is that in the mapping phase, on the mapping machines, in the mapping slots, we have an extra workload after we've applied the map function. We combine the intermediate key values into less intermediate key values. Now, the way it's done and the moment where it's done, it's without any guarantee. So you can suggest a combined function to MapReduce. We'll see how we do that. But MapReduce will not guarantee you anything. Maybe it's going to call it just once when it spills to disk, right? Maybe it's going to call it every time it flushes and every time it compacts, which is the natural thing to do. Or it will not even call it at all. You have absolutely no guarantees. This is just a suggestion that you kindly make to MapReduce, saying you could, by the way, use this combined function if you want, but there is no guarantee. All right, and again, does it make sense, right? That it's when we flush and we compact that we can do it. Because when we flush and we compact, the key values are ordered already and grouped by key. So it's a natural thing to do, to call these groups with the same key to reduce them to a single key value. So this is what my combine function does. Now, very, very, very often, I would say in 80% of the cases, the combine function is actually the same as the reduce function. We just use the same implementation. But there are two assumptions under which we can actually do that. And these assumptions are, the first one is we must have the same types for the intermediate and output key values. Otherwise, it doesn't make sense, right? Because you cannot use the reduce function to map intermediate to intermediate, because intermediate to intermediate must be the same type. So if you use the same as the reduce function, then it means the output type must also have the same type as the intermediate type. Am I making sense? Right? Okay. So that's the first assumption. If we don't have the same type for intermediate and outputs, then we cannot reuse the reduce function as a combined function. My second assumption is that my reduce function is both commutative and associative. What do I mean with that? I mean, in the case of the sum, when we were just summing the counts of the Pokemon, this is commutative and associative. The sum, addition, is commutative and associative. Max, min, is also commutative and associative. Big warning, average is not. If you try to use the average of the values, be very careful. You cannot use that as combined because this is not associative. It's commutative, but it's not associative. All right? Okay, so big word of warning. It must be this. Now, if you're a mathematician, you might not be satisfied with me calling the reduce function associative and commutative, because mathematically speaking, if you consider it mapping key values to key values, that is not strictly speaking the right way of calling that. But it's just the intuition that whatever operator you use in order to aggregate the values on the right side must be commutative and associative. Right? That's the idea. All right. So this is the spirit of the optimization of bringing the query to the data, because we aggregate the key values as early as possible, as close as possible to where the data comes from. So let's do it on an example, and you will see it will make sense. Imagine that I'm counting the words. That was the example I had earlier. And now for every line of text that I interpret as a key value, I produce one intermediate key value with the word as the key and the one as the value, always a one, right? So it's one occurrence. Now my reduce function was a sum, right? I was computing the sum of the ones. Now sum is associative and commutative, and the key value types are the same in the intermediate and output key value pairs, because it's always a string as a key and a number as a value. So I'm checking all of the boxes. So it means that I can use that sum function that I'm using to reduce my key value pair. I can suggest MapReduce that it could use it as a combined function. So now what's going to happen, imagine that I overload my memory completely because there are so many of them. Maybe it was what we call a stop word like V, A, B, is. So imagine that I had to flush the memory at that point. Then I will call, or MapReduce can, but is not obliged to call the combine function and store instead lorem3. So you had this in memory, lorem1, lorem1, lorem1. But when you flush it to disk, you call the combine function on the fly and only store lorem3 to disk, right? Here I flushed again with 4 ones and I store to disk 4. Then I again do it like this with 4, 2, and so on. And then when I reduce, I have less intermediate key values, and you see the network will be less overloaded because this is what will travel over the network now, not this. Without combine, it would have been all of this. But now we reduce the traffic on the network, right? So when I say it's when we flush that we combine, it's only an example. Maybe you do it directly in memory, you don't even flush, right? Maybe you notice you have a lot of keys in the memory, and then in the memory, you replace this with this, and you don't even flush, right? But all of that is basically as MapReduce wants it, right? You have no control over that. This is whatever MapReduce wants to do, and it could even change between versions. All right, so you're kindly suggesting the combine function, and now you see there's less traffic over the network, and the whole MapReduce job will be faster. Who understands that it makes it faster? Right, awesome. So less key values. And does it answer the question you asked earlier? Okay, that's exactly it. All right. Now, still have 5 minutes. Maybe I can just quickly say that MapReduce is implemented in Java. So it runs on the JVM, and one of the natural languages you can use is Java to implement your code. But there are all other languages supported, like Python and so on. It's called the streaming API. But I will not go too much into details regarding this. It's almost using the SCD in and SCD out for the implementation of the map and the reduce function. So basically, you can consider that the map function is reading from SCD in, implemented as some sort of bash script or Python script that outputs back the intermediate key values to SCD out. Right? That's kind of the way it works. But I'll not talk too much about that. I'll talk more about Java. So here's how it looks like in Java. You basically define a class that you call typically mapper or my mapper or whatever name you want to give it, but it extends mapper. And then you implement a map function that takes one key and one value from the input. And you have, because it's an imperative language, context write, new key, new value, and you can call that 0, 1, or more times, as often as you want. Every time you call context write, it's going to create an additional intermediate key value. Then you have the reduce function. The reduce function is typically implemented in a class that you call reducer. That's the name of the class. And there is a reduce function. And here you have to pay attention to the signature here, because the reduce function must be called once for every distinct key. So what I have here in my parameters is the key itself, and then a list of values, right? So here, because we want to stream through them, we just take an iterable, which is just a way of the next, right? But you basically get all of the values associated with that key. And inside the reduce function, you can write context write as many times, 0, once or more as you wish. Very often, what this does is new key equals key, and new value is just the sum of the values in the iterable, and then you write just once the new key and the new value for counting, for example. Okay. And then in the main function, you know, in Java, you have this main function that is executed when you execute your program. You just use the setMapper class, setReducer class to say what you want. You say what's your input path on HDFS that you want to read from, what's the output path that you want to read to, and then you just exit after waiting for the completion of the job. And when it exits, then you can just look at HDFS and wow, wonderful, the data is there, the output data. All right, if you want to combine, and let's say you want to reuse the reduce function as a combine function, just use setCombiner class. And again, it's a suggestion that you're making to MapReduce, no guarantees. It's a suggestion that you can use this combine function. Okay, I'm going to stop here today, and next week, I'm going to come back on the tricky points, but the summary of that is never use the words mapper and reducer. I'll tell you exactly what terminology to use, and by doing that, it will make it crystal clear in your mind what's actually going on in the cluster. All right. So thank you very much for attending today's lecture. Enjoy the exercises curated by the TA team. I'll see you next week at 2 p.m. for the continuation of this lecture. Thank you very much.